hace un ruido.
Luego lo apagamos como ayer, porque si no, entre el ruido y que hace mucho frío,
Sí,
ahora
aquí.
está que vaya enfriando y ya está. Si no hace tanto calor tampoco. Pues, podemos tener medio sí, de la cosa de Suiza. Cada sí, Suiza. Quiero preguntar también a la institución suiza. Sí, sí, es verdad, sí, me dijiste. Nosotros aquí tenemos hasta las 11. Ok. A las 11 es el café, pero yo tengo que recibir a un profesor de Málaga y estaré con él supongo que hasta las 12 o 12:30 por ahí. Yo me quedo hasta mañana. ¿Tú te quedas? ¿Mañana te quedas también? Mañana me quedo. Vale. Mañana tarde me voy a nada. Y luego mañana tarde. Sí. Vale, yo de todas formas, vamos a intentar que sea hasta mañana, ¿vale? Vale, vamos más seguro. ¿Cuándo puedes? Sí, pues bueno, tú quieres ir a los training, a los dos training que hay de fotometría y de... ¿Dónde te quedas por la tarde? ¿Dónde vives? ¿Dónde estás parando? ¿En hotel? En Hotel Sevilla, a calle Granada, arriba del paseo. Sí, ya se lo dejo. Pero, digo, estoy donde quiera. Donde quiera se puede caminar. Eso. Sí, sí. Si no, a lo mejor te... Ahora lo miraré en mi agenda y si no, quedamos esta tarde. ¿Vale? Porque como Máximo también se va, Elisa también, me quedo más o menos libre esta tarde. Tengo una reunión de 4 a 6, pero podemos quedar a las 6 de la tarde, por ejemplo. Cuando quieras. ¿Vale? Sí, sí, vale, vale. Sí, sí, la tenemos. Sí, la versión nueva tendrá. En el escritorio, en la carpeta de presentaciones,
Sí,
métela dentro de ahí.
vale.
Pero como esto es una pantalla digital, no señala.
Ah,
Me explico, si quieres señalar tiene que ser con el ratón,
vale, pues.
¿vale?
Y se
Pero
puede ver. O esto también funciona.
esto funciona. Si quieres también hay uno de estos de solapa. Si quieres
No,
sentado,
no, no, no. No, sentado.
pues te pido el micrófono
No,
de solapa.
no, no, no pasa nada. Bueno, eso también funciona.
Sí, sí, está encendido ahora, ¿no? Los botoncitos verdes, eso. Está encendido. Si te pones aquí, está perfecto. Pero va a tener que estar muy pegado para que te escuche.
Vale.
O sea, te dices de solapa, si no, pues no.
Que no me siento raro con esto. ¿No?
Sí, sí, lo encenderemos. Iba a encenderlo ahora después. Vale.
Gracias. Para que firme y lo vayáis pasando. Y ahora firmas tú también. Sí. Yo no sé si ponemos.
Morning.
Ahí voy con
Serena, can you hear me?
Yes, I can hear you. Is
Okay,
everything
perfect.
fine, Gabriel? Do you need something from me?
No, no. I will send you the last version of the presentations, including the one from David
Yeah,
yesterday,
yeah,
because okay, and everything is fine. I think
yeah,
that the people enjoy the city, enjoy the course, the university, because they are working a lot around the university.
yeah. Great, great. Yeah, I got some good comments yesterday also from participants online that they enjoyed. Yeah, the classes. Everything is fine with the signature list.
Yes, we already collect the
Yes.
signature yesterday, and today we'll finalize the process.
Okay,
Yes.
great,
Also,
perfect.
we take the picture of the group and
They
a
have
lot of
now seen it.
pictures during the event.
Yeah, yeah. Thanks. Yeah, I've seen it. Yeah, this is really nice. We made the communication on the social media also. They are out. Okay, perfect. Okay, I'm online. So if something is needed, just yeah, make me a warning, and I'm here.
Okay,
Thank
thank
you.
you. Still, we have 4 minutes to start the session today. Did you enjoy the city yesterday? Yes. What do you think about tapas? Ah, churros. Ah, churros. Okay. Yes, yes. You know that at least in Spain, also in Italy, we eat a lot. All the dishes are quite contundent, quite large. But in Almeria, the most typical is to share some fish, especially small fishes.
like boquerons, salmonetes, this type of small fish are the typical ones. Not large tuna or something like that, which is more regular from other countries, etc. Or salmon or this type. I suppose that all of you have your plane or your return back this afternoon, right? Tomorrow, okay, perfect. Then this afternoon you have the opportunity to visit the city or to enjoy the beach, etc. Today will be a very hot day because there is no wind and it's very sunny, very pleasant to go to the beach. But be careful about the temperature because it's quite hot. Okay, uh, we will start. I think that students are still coming, but to follow the program, we will start the session. This morning we have two excellent presenters, two really nice experts. Ana Sanchez Urano from the University of Murcia, but previously from here, from the University of Almeria. She will present the advances in or the use of photorespirometry for the monitoring of microalgae culture and how we can use this technology for different purposes, modeling, etc. And it's a pleasure for us to also have here Massimo Pernice from Instituto of Marine Science from Barcelona. This group is really recognizes or they have a large expertise in evaluation of samples in ecological samples in ecological ambients, and then to elucidate the interaction between this type of microorganisms or in these populations, etc. Then Massimo will explain us about how to use flow cytometry and especially for this type of applications, identification of parasites or microalgae-related processes. Then I don't want to use more time. Please, Ana. Espera que voy a repetir esto.
Esto no se ve aquí.
Ok.
El puntero.
El puntero es que en la pantalla no se
Vale,
muestra.
vale. Bueno, si no señalo con la mano.
Sí, ¿ya funciona?
Sí. Ok. Good morning. My name is Ana Sanchez Zurano. As Gabriel said, I am a professor in the University of Murcia, but I did my PhD here in Almeria. Before starting the presentation, I would like to send the organization, the organizer of the PARAQUA course, Serena, and the local organizer, Gabriel. Also, I want to send the on-site and online attendees. As I mentioned, I did my PhD here in Almeria in the Gabriel group, and my PhD was focused on modeling microalgae bacteria interaction in microalgae-based wastewater treatment system. During my time in Almeria, we tried to develop a rapid, simple, and economic technique to study the microbial interaction that appear in microalgae culture, especially in microalgae wastewater treatment system. For this purpose, we focus on phytorespirometry as a rapid technique to characterize algae cultures. So I would like to introduce you today this technology and the more useful application of this technique. Okay. Well, respirometry is not a new technique. Respirometry is a really useful technique used in activated Slack processes to study the heterotrophic bacteria activity and the autotrophic bacteria activity. Also, photorespirometry is used in natural environment to study the photosynthetic activity of phytoplankton. And currently, is a promising technique to characterize the algae-bacteria interaction that appear in a microalgae system, especially in large-scale microalgae system, in which microalgae establish a relationship with bacteria. And what is the common factor, all of the variation of respirometry or photorespirometry? So the more important factor is the dissolved oxygen, because we know that when we are working with algae culture, the dissolved oxygen concentration increase under illumination and decrease under dark condition by the respiration activity. So using dissolved oxygen, we try to standardize the photorespirometry technique. Photorespirometry, as I say, is a technique to determine the photosynthetic activity and the respiratory activity in algae culture through the dissolved oxygen concentration in the culture. For this purpose, we use light and dark cycle that allow us to determine these two activity or these two phenomena in algae culture. Using this methodology, we found different applications, and today I will introduce you two of the more useful applications, especially when you are working in large-scale microalgae facilities. One of the applications of photorespirometry is to study the influence of environmental and operational variables like temperature, pH, light on microalgae activity. Because depending on this condition, algae respond, the photosynthesis of algae responds. So with photorespirometry, we can determine the influence of this parameter or this factor easily. The other important application is to study the consortia that appear in microalgae-based wastewater treatment system between microalgae and bacteria. When we are producing algae with wastewater, or when we are treating wastewater with algae, interaction between algae and the organisms that appear in wastewater are stabilized. And with this technique, we can study the interaction between algae and bacteria. And normally, the bacteria that we study with this technology is heterotrophic bacteria and nitrophilin bacteria. Well, let's go to study the two applications. The first one application is the use of photorespirometry to study the influence of environmental and operational conditions on microalgae activity. We know that when we are producing microalgae in photobioreactor, both in indoor photobioreactor or outdoor photobioreactor, different parameter or factor appear and determine the growth of algae. The first one parameter is the light. Light determines the growth of algae. It's the most important factor, but the influence of light is modulated by the other parameters as temperature, pH, dissolved oxygen, and also the nutrient concentration. The nutrient concentration, the main nutrient that we study normally are nitrogen and phosphorus in algae culture, and in bacteria, also the influence of organic matter. So in traditional experiment, when we want to study how this variable affect algae growth or biomass production in a photobioreactor, we have to do time-consuming experiment in which we are monitoring every day the growth of algae. But we propose an alternative using the photorespirometry. Using the photorespirometry, we can determine the photosynthetic activity of algae and relate this photosynthetic activity with the biomass growth. For this purpose, we have to focus in the photosynthesis process. We know that microalgae are photosynthetic microorganisms, and during the photosynthesis, microalgae use carbon dioxide as a carbon source and sunlight as an energy source. And in this process, dissolved oxygen is releasing and microalgae biomass is produced. These are the principal phenomena that appear during the photosynthesis processes, and this processes is schematic in the photosynthesis formula that we have here. In this formula, we know that we need 6 mole of carbon dioxide, 6 mole of water, light, and we can produce 1 mole of biomass. In this case, we put sugar, but a simplification of the biomass. And also, we can produce 6 mole of dissolved oxygen. So if we have a technique that allows us to monitor easy parameter as dissolved oxygen, we can relate the dissolved oxygen with the biomass production, because we know that if it's 6 mole of dissolved oxygen is related with 1 mole of biomass. So photorespirometry is a technique that allows us to measure the dissolved oxygen concentration or the dissolved oxygen production in the culture and relate this dissolved oxygen production with biomass using this stoichiometry. How we can measure this activity or the dissolved oxygen production? We know that microalgae perform 2 different activities: photosynthetic activity and respiratory activity. Under illumination, we know that algae perform photosynthesis, while in the same time perform respiratory activity. So under light condition, we have these 2 phenomena, photosynthesis and respiration. However, when we expose algae under dark condition, we only have the respiratory activity of algae. So if we can determine the dissolved oxygen production in lab during the light phases and dissolved oxygen consumption during the dark phases, we can determine the microalgae photosynthetic activity, or only the microalgae activity take account these 2 phenomena. To determine these two activity, it's easy. We can take a flask, we can add a culture, we use a lamp, and we take a dissolved oxygen proof, and we measure if the dissolved oxygen increase or not increase. But we have a more sophisticated equipment that allow us to control the condition in which we want to measure this activity and change this condition if we want to test different options. This equipment is the photorespirometer. Here in this slide, we have a schematic figure of the respirometer, but during the last part of the course, we will go to IFAPA, and in IFAPA, you will see the real photorespirometer and the methodology that we use to determine these activities. The respirometry consists on a jacketed and stirred flask here with LED lights on both sides, on the right and on the left, and also the flask. In the flask, we have different proofs. The proof that we have here in the respirometer are the light proof, the temperature proof, pH proof, and also we have an air bubble. These proofs are essential because the light proof is totally necessary because we have to know the average light inside of the culture, because with the sensor we can monitor and control the light intensity in the middle of the culture. Also, we have the temperature proof because maybe we want to know the algae activity at 20 degrees, at 40 degrees, at 10 degrees, and with this proof we can measure the real temperature in the culture. And to regulate the temperature in the culture, we use a bath. Also, we have a pH proof if we want to test the activity of algae at different value of pH. And we can regulate the pH. We have different methodology to regulate the pH. Some group use acid and basic, and other group regulate the pH with carbon dioxide. In the Gitme, we have an air bubble. We have an air bubble because in some experiment we want to know the algae activity at different dissolved oxygen concentration, or also we want to start all the experiment in the same dissolved oxygen concentration. So these air bubble are useful for two applications. All these proofs are controlled by LabJat, and LabJat is connected to the computer. Using the computer, we can monitor the variable in real time, and also we can change some condition in the photorespirometer. Well, this is the Gitmen that we normally use, and also we have a methodology, or a standardized methodology that we apply to measure the microalgae activity, taking account the oxygen production during the light phase and the oxygen consumption during the dark phase. Okay. In this slide, we have a schematic figure of the methodology that we normally use. To measure the oxygen production rate and the oxygen consumption rate, we need to apply dark and light cycle. In this dark and light cycle, we will measure the dissolved oxygen concentration in the culture. Normally, each phase, dark phase and light phase, take 4 minutes. In these 4 minutes, we measure the oxygen production or the oxygen consumption. For the mathematical calculation in the program only takes the 2 last minutes, because the first 2 minutes of each phase is considered that is adaptation time. So you apply cycle of dark and light condition. Each cycle take 4 minutes, and we discard the first 2 minutes, and we take the last 2 minutes to do to determine the rate. In the first case, in the dark phase is the oxygen consumption rate, and in the light phase the oxygen production rate. To start the experiment, we always start in the same point. What is the same point? We want to study the activity in the saturation condition. I mean, we start each experiment at 100% of dissolved oxygen saturation. That is this point. Here we start the test, and firstly, we expose algae under dark condition during 4 minutes. In this 4 minutes, the dissolved oxygen concentration decreases, and when the test finishes, the Gitmen stop the measurement, and the air bubble starts. The air bubble starts up to the saturation, up to 100%. When the dissolved oxygen concentration reaches 100%, start the new phase, that is a light phase. In this light phase, we observe that the dissolved oxygen concentration increases. After 4 minutes, the equipment stop and the airproof start to bubble air up to reach again the saturation. So we apply this cycle 3-4 times because we want to determine 3-4 values of oxygen production rate and oxygen consumption rate to do the average. In this slide, we have a experimental value of typical photorespirometry. And here we can observe that the program registered a different value. The first one that we have here, this is the oxygen consumption rate. As you see here, the oxygen consumption rate is measured in oxygen milligram per liter and per hour. This is the real value that the program or the system gives us. This value is a negative value because it's a negative rate because the dissolved oxygen is consuming in the culture. Also, here we can see the temperature and the pH during the test. Here we have the temperature and pH during the dark phases. The temperature in this experiment is close to 25 degrees because we control the temperature with the bath. Moreover, in this table, we can see two values related with the light or with the radiation because we fix the radiation in the culture. In this case, is the first this column. Here we observe that we fix the radiation at 500 microesten per square meter per second. And in the next column, we have the real radiation in the culture. So on the equipment, I think it's worked very well because it's the same. In the respirometer, give us the oxygen production rate that is this value that is a positive value because the oxygen is increasing in the culture, and also the temperature and the pH during the late phases. During the training, we will see this table and we can study all these variables. Okay. Using this experimental data, we perform different analyses. The first analysis is to determine the real microalgae photosynthetic activity or the microalgae photosynthetic rate. For this purpose, we have to consider the two activities that we measure, the oxygen production rate and the oxygen consumption rate. These rates are in oxygen milligram per liter per hour, and we want to normalize this value. So we determine the real oxygen production rate and oxygen consumption rate divided the rate by the biomass concentration, because we perform a test at 20 degrees, 25, and maybe tomorrow we want to compare this data with other experiments performed at 30 degrees. So we need to normalize the data by biomass concentration. So when we normalize the oxygen production rate and oxygen consumption rate, we can determine the microalgae photosynthetic rate as oxygen production rate minus oxygen consumption rate. So this is more or less the methodology that we use or we apply to determine the activity of algae under the influence of different environmental or operational conditions. This methodology is not only useful to determine the response of algae at different temperature or different concentration of nutrients. Also, if we have a culture and in the culture appear a predator or a fungi parasite, we can observe doing a photorespirometry that the activity of algae decrease. So it's a useful technique not only to detect the influence of operational factor, also the system of different predator or contaminant or something like that. Okay, now I will introduce you some example of this methodology or this technique. In this first case, we study the microalgae photosynthetic rate of 3 different microalgae strains with different industrial interests, as Steneresmus almeriensis, that is our algae, Chlorella vulgaris, and Nanochlorosis galitana. We perform this test at 30 degrees, and we study the response of the three strains at different irradiance from 0 to 2000 microstrain per square meter per second. In this table, we can observe the microalgae activity of each strain. Here we have the microalgae activity, not the oxygen production and oxygen consumption. It's the final microalgae activity, taking account the 2 phenomena, the photosynthesis and the respiration. Here we have the experimental data that we obtain and also the standard deviation. If we represent this data, we obtain a figure as we have here. In this figure, we have the irradiance and also the microalgae activity or the microalgae photosynthetic rate. If we look this experimental data, we observe that the microalgae activity increase to a point in which remain constant. And using this experimental data, the next step is modeling this experimental data. This part is really related with the Enrique presentation that he did the presentation yesterday, and we were in collaboration. And when we have this experimental data, we start the modeling process. In this case, we model this experimental data using the growth model, but now is a photosynthetic model of Molina. That is the equation that we have here. In this equation, we observe different parameter or characteristic parameter as the maximum photosynthetic rate, that it will be as the maximum biomass growth. And also we have the irradiance, the light affinity constant, and N, that is a shape parameter. If we model our experimental data using this mathematical equation, we can obtain the value of the different parameters and also the representation that we have here. This modeling approach is really useful because you can compare the maximum photosynthetic rate of the 3 strains at the same temperature. So it's really useful when you want to apply this in a real system, because you can estimate your productivity, because as we say in the photosynthesis slide, we can relate this maximum photosynthesis rate with the maximum biomass production or maximum biomass growth. Well, I think okay. Now we will see another example of the application of this methodology. This example was using in a paper or in a work that Enrique and we did in collaboration. And my part was in the lab to study the influence of temperature in different algae strains, in 5 algae strains: Spirulina platensis, Chlorella vulgaris, Nanochlorosis galitana, Isocrysis galvana, and Steneresmus almeriensis. For this strain, I performed some photorespirometry experiments, and we observed the response of the algae at different temperature value. To obtain the experimental data, we model this data using the cardinal equation. using this cardinal equation, we can obtain the optimum temperature, minimum temperature, and maximum temperature for each algae. Studying the influence of temperature on microalgae strain, we study the influence of light in this strain, and we study the influence of light on this strain using the optimal temperature for each algae strain. When we perform this experiment, we obtain different experimental data, and we feed this experimental data with the Molina model or with the Molina equations. Also, we obtain the characteristic parameter that the more important as the maximum photosynthesis rate and the constant affinity. In this slide, we can observe some of the experimental data, the experimental data that we obtain after the modeling processes. Here, I selected the optimal temperature for each algae, and we observe that the optimal temperature of each algae is close to 30 degrees. We study Semedesmus, nanochlorosis, chlorella, spirulina. The highest optimal temperature was for Spirulina platensis. And what we can do with this data? With this data, Enrique performed some model approach in which he tried to determine the optimal depth of the culture in each season depending on this result. Because if we know the optimal temperature of each strain, we can try to control the reactor to manage it in this optimal temperature. To have a temperature control is not easy, but you can apply different strategies as regulate the depth or the depth of the culture. For this purpose, we take the environmental data of Almeria in different seasons. Enrique performed the model, and this model allows us to know what is the culture temperature and the oxygen production rate of each algae depending on the environmental temperature in Almeria. And also, we can relate the oxygen production with the biomass productivity. And the final part was to select the optimal deep culture to maximize the biomass productivity, because algae will be exposed under the optimal temperature for each algae. Well, now we will see briefly the other application of photorespirometry, that is study the interaction that appear between microalgae and bacteria in microalgae-based wastewater treatment system. Microalgae, under light condition, microalgae release dissolved oxygen, and the dissolved oxygen is used by bacteria. Bacteria within the bacteria group, here in our area, we distinguish two main groups: heterotrophic bacteria and nitrifying bacteria. Heterotrophic bacteria are capable to consume or degrade organic matter using the dissolved oxygen produced by algae. And nitrifying bacteria perform the nitrification process in which ammonium is oxidized to nitrates. The activity of these three main groups, heterotrophic bacteria, nitrifying bacteria, microalgae, is a coordinated activity because each group contributes to the consortia. And we try to study the contribution of each microbial group using the oxygen consumption and the oxygen productions. And using this idea, we improve the traditional photorespirometry to try to identify how each group contribute to the consortia. For this purpose, we part the same that we saw in the last slide, because we can determine the microalgae photosynthetic rate using a cycle of light and dark condition. And now, if we want to study the heterotrophic respiration rate and the nitrifying respiration rate, that I mean the heterotrophic activity and the nitrifying activity, we can use a specific substrate. For determining heterotrophic activity, we can use sodium acetate, because if we add sodium acetate in a microalgae bacteria culture, bacteria start to consume the acetate and the dissolved oxygen concentration in the culture decrease. This idea is the same for nitrifying bacteria. We know that nitrifying bacteria oxidize ammonium. So if we use a substrate as ammonium chloride, we can observe that the dissolved oxygen concentration in the culture decrease because the bacteria are consuming the nitrogen, or it's performing the nitrification process. So taking in mind this concept, we use a specific methodology in the photorespirometer to determine these activities. The first activity that we determine using the photorespirometer is the same that we saw. We apply a cycle of light and dark condition to determine the microalgae activity. When we determine, after determining the microalgae activity, we start to determine the heterotrophic activity. For this purpose, we use a new culture that is the same that we used previously for determining the microalgae activity, and we add the sodium acetate. When we add the substrate, we observe that the dissolved oxygen concentration in the culture decreases, because here we have two respiratory activities: the respiration, the endogenous respiration by algae, and the respiration by bacteria, because bacteria are consuming these substrates. So using this response, we can determine the heterotrophic activity. The same idea is used to determine the nitrifying activity. For this purpose, we take another sample, we add the sample to the respirometer, and we add the specific substrate for nitrifying bacteria. When we add this substrate, we observe also that the dissolved oxygen concentration in the culture decrease. And this oxygen consumption is because the algae respiration and the nitrifying bacteria respiration. Now, when we perform different tests using this methodology, we start with the mathematical calculation to determine the activity of the three groups. And here we have the mathematical, or the mathematical part. The first one is the same. We use the oxygen production rate and the oxygen consumption rate to determine the microalgae photosynthetic rate. For this purpose, we normalize the respirometer data using the biomass concentration of the culture. After that, to determine the heterotrophic activity and the nitrifying activity, we use a new parameter. This new parameter is the heterotrophic consumption rate that we measured in the previous slide in this part, in this dark phase. In these dark phases, when we add the substrate specific for heterotrophic bacteria, we obtain a new rate. And this rate, we use this rate, we normalize this rate using the biomass concentration, and we use this for determining the heterotrophic activity, because the heterotrophic activity is the rate that we determine using the substrates minus the oxygen consumption rate during the dark phase in the microalgae endogenous respiration. So we apply this methodology to determine the heterotrophic bacteria activity and also the nitrifying bacteria activity. In one case, using the sodium acetate, and the other case, using the ammonium chloride. This methodology will be applied in different algae bacteria culture, and we can compare the result because sometimes we want to potentiate the microalgae activity, but maybe in other case we prefer to potentiate the heterotrophic activity. I mean, when we have a wastewater with a high organic matter concentration, maybe we want to potentiate the heterotrophic activity to degrade the organic matter. In this slide, we can see an example of this methodology. And in this case, we determine microalgae activity, heterotrophic bacteria activity, and nitrifying bacteria activity from different microalgae system or microalgae culture. In this case, we have a freshwater culture, a microalgae bacteria culture using pig manure or pig slurry as a nutrient source. Also, we study the microalgae bacteria consortia in a system fed with primary domestic wastewater, and also using agriculture leachate. We study these three activity in this sample, and in this graphic we have the result that we obtain. Here we can see microalgae activity, heterotrophic activity, and nitrifying activity. For me, the most important conclusion is that the microalgae contribution is higher than the bacteria contribution, and in all cases, it's the same result. When we have a mixed culture microalgae bacteria culture, in terms of oxygen production and oxygen consumption, algae is the one, always. And now we can compare the activity of the bacteria between the different effluents, because we observe that in agriculture leachate, we obtain the maximum heterotrophic and nitrifying activity, but in this type of wastewater, we have a high level of organic matter and high level of ammonium. So it's a normal or expected result. Also, we can use this methodology not only to determine the microalgae and bacteria activity in algae system. We can use this methodology to model the influence of environmental factors as light, temperature, or operational factors as pH, dissolved oxygen on microalgae activity, and also on heterotrophic activity and nitrifying activity. In this work, we perform the same analysis or we perform the same methodology that we saw previously, to study not only the influence of temperature on microalgae activity, and also on heterotrophic activity and nitrifying activity. We obtain different experimental data, and we fit this experimental data using equation as the cardinal equation. This same approach we were used to determine the influence of pH on microalgae, heterotrophic bacteria, and nitrifying bacteria. And also, all of these experimental data were fit with the cardinal equation. The same for the dissolved oxygen concentration. And we perform the photorespirometry experiment, changing the dissolved oxygen concentration and in the culture, and we observe the response of the three groups. All of these experimental data were fit with the proposed equation. Okay, after all the experiment and after modeling all of these response, here we have a summary of all of the results. if we look this result, we can see that the optimum variable for each group is different. I mean, in the case of temperature, we observe that the optimum temperature for algae is more or less 30 degrees, for heterotrophic bacteria, 36 degrees, and 33 for nitrifying bacteria. So here we see that if the temperature in the culture increase or decrease, the consortia, the relation in between microalgae bacteria in the consortia also change. So this methodology is really useful to study the influence of this variable and to have a rapid technique or a rapid method to change or to comprovate the interaction between the microorganisms. Finally, I would like to introduce you briefly a result from a work or a paper that we did in collaboration with a group in Milano with Elena Ficara and Simone Rossi, because I performed my international stay during the PhD in Milano, and we collaborate to improve this methodology, because we were using photorespirometer, but also in Milano, this group are really expert in this methodology, and I really learned with them. The improvement of the methodology was to divide the nitrifying bacteria. I say that nitrifying bacteria oxidize ammonium to nitrate, but in reality, this process consists on two steps. The first one is performed by ammonium oxidizing bacteria, in which ammonium is oxidized up to nitrite. And in the second step, the nitrite is oxidized up to nitrate by the nitrite oxidizing bacteria. In this work, we try to model these two activities, the two bacteria activity, the ammonia oxidizing bacteria and the nitrate oxidizing bacteria, and also to model the influence of environmental factor on heterotrophic bacteria. We not only modeling this activity in algae bacteria culture, but also in activated sludge processes, because we wanted to know if the activity of this bacteria is the same or is different if we use algae in the system or we don't use algae in the system. Here we have a figure that in which we can see the parameter that we test and the range of this parameter, and we test the influence of temperature, pH, dissolved oxygen, and also the main nutrient concentration that appear in the wastewater. And in the next slide, we have a different figure in which we can represent the experimental data that we obtain and also the modeling that we apply. And in this case, we have the influence of temperatures on heterotrophic bacteria, ammonium oxidizing bacteria, and nitrate oxidation bacteria. This figure includes also this activity in activated sludge processes and this activity in microalgae bacteria processes. And we can observe that in some cases the behavior and the different temperature condition is the same, but in other case, the optimal temperature and the minimum and maximum change depend on if we are using only activated sludge or if we are using a microalgae culture. This is the same for the pH. We also evaluate the influence of the pH, the influence of the dissolved oxygen. All of our experimental data fit with different models, and we model the influence of nutrient concentration of each bacteria groups. And I don't want to extend more in more time. So to finalize, I would like to say that photorespirometry is a really useful, rapid, and economic technique that allows us to characterize microalgae bacteria consortia and to distinguish the contribution of each group to the consortia, and also to study and to model the influence of the culture condition on microalgae, microalgae and also on different group of bacteria. So thank you so much for attending today.
Thank you. Thank you, Anna, for the excellent presentation. Plenty of data.
Yes, too much.
No, it's very interesting. Now we have time for questions from the audience. Yes, Daniel?
I didn't understand because in the beginning you said that photorespirometry is not a new technique, so
No, yes.
but I didn't understand if the setup you explained is a commercial setup or something you developed here.
It's a equipment that we developed here, but other groups are also developing other kind of photorespirometer, but the objective is the same. So the technique is not a new technique; it's a classical technique. But now we have a more sophisticated equipment, and we have standardized the methodology.
But it's not a commercial
No,
equipment.
it's no.
I don't.
It's a handmade equipment.
Yes.
Oh.
As I know, there is no companies commercializing this equipment.
Yeah, I remember a long time ago I used to use one with a pen
Yes.
yeah, it's very nice.
Now the equipment that we are using is more robust and more reliable because we developed with the colleagues from the informatics department, and then
Yes.
all the signals are better managed, etc. And the precision of the methodology increased a lot.
Do you intend to commercialize it?
Yes, but we always find the same problem. We need a company that is able to do that because we cannot put the students to build the equipment. And then we are trying not only for this purpose, but other developments that we have to find companies interested to commercialize this type of equipments.
Okay. Thank you.
More questions?
Serena.
Please, Serena, I think you can participate directly.
Yeah, hi, Hannah. Thanks for the presentation. Yeah, I'm wondering if you it happens to you to test the method on some contaminated culture, and you think it can be also a method that can be used for the early detection of problems and this kind of issue that can arise with the culture production.
Yes, because this technique is really rapid, so you can use this methodology to monitor every day your culture. And if you detect a decreasing in the microalgae activity, you can try to relate this process with some predator or contaminator, or maybe it's an environmental influence. But you have the tool to say, how I have a problem. I try to find what is the problem.
At this respect, I think that we must to consider that we need to integrate different approaches. I mean, by sure, omic techniques will be the most sensible to detect the presence of this pathogen or whatever. Using respirometry, as Anna already mentioned, we are able to, to monitor the performance of the culture. And then if the culture is performing well, we will always obtain a certain value of photosynthesis. In the moment that we have a problem in the culture, we will observe a decrease in this performance. The advantage of this photorespirometry technique is, as Anna mentioned, is very fast. It's only to take the samples, to put in the vessel, and to push the button. Then in 20 minutes, you obtain the measurements about the real performance of the culture. But by sure, we will be able only to detect that there is a decrease in the performance once the problem achieve a certain proportion. For early detection, I think that we need microscopic tools or omic tools or something like that.
It's complementary. Yeah. It's more precision than would be needed. Okay. Yeah, I see. Thank you.
There is another technique that we use is fluorescence of chlorophylls. This technique is also very useful for that. But the major disadvantage of fluorescence of chlorophylls is that you must to measure in the reactor. Because if you take the sample outside, you are more or less avoiding the conditions in the culture. You are measuring the performance. It's similar to photorespirometry, yes, certain conditions. It's also very fast. It's always we need the complementarity between these techniques.
Yes.
More questions? I want to I take some notes about the presentation. I want to remark one important point. One of the advantages of photorespirometry is that we measure the real status of the samples of the cultures at the condition that they have in the reactors. Then we can mimic these conditions, and then we evaluate that. Or, as Anna mentioned, we can modify the conditions, more or less considering the complete range of conditions that the reactor can suffer along the day or different season, etc. But don't forget that also timing is very important. I mean, if you expose the cells to 35 degrees for a few minutes, as you already see in the presentation, we obtain very nice performance of the cell. But if you provide 35 degrees or 40 for 2 hours or 6 hours, probably the culture will die. Then photorespirometry is a technique to evaluate the immediate effect of the parameters. If you want to study the accumulation of these effects, you must perform the photorespirometry at different times, okay, to mimic or to know which is the evolution of the cultures.
Yes, we try to do a model that include temperature and time. Yes, we have experimental data, but we didn't finish. Maybe in the future we have to focus
Yes,
on
we are working.
integrate the two.
We are working on that.
Yes.
to include in the models the dynamic behavior of the cultures. Then how much or how long the culture were exposed to certain conditions, and then it's the same that us. We cannot measure or grow if we take breakfast in the morning or lunch. It's a consequence of the entire lifestyle. Then it's more or less the same. To try to integrate in these models not only the static values of the parameters, but also the dynamic and the history of the culture. Okay, but this is a next step in the modeling. Yes, I have another question. We have time? Yes, 3 minutes. Very important. Anna explained that the measurements, and some people measuring performing photorespirometry, they measure milligrams of oxygen per liter and per day or per hour. Is the amount of oxygen that is produced in the vessel. Okay, but to really use properly these numbers, we need to normalize to the biomass concentration. Then don't manage milligrams per liter and per day, because if the biomass concentration in your samples modify, your final response modify. Then to make the measurement intensive, you need to normalize dividing by the biomass concentration. Well, what is biomass? Biomass is the amount of solids that we retain using a filter, the normal dry weight that we perform. But when we move from algae reactors to algae reactors containing wastewater or whatever, we observe and already demonstrate that we have bacteria. It's necessary to normalize the measurements to the amount of bacteria that we have in the reactors. We were discussing this point for a long time, and we conclude no, because we don't know how much bacteria, algae, or whatever we have in the solids. And at the end, this is the regular measurement. And then we always divide the oxygen production by the total biomass we have. We don't differentiate between bacteria or fungi or algae or cyanobacteria or whatever. We cannot do that. And from the engineering point of view, this is the most reasonable approach. Of course, with the help of ohmic techniques, we can try to find this or to evaluate the number of this proportion of bacteria, proportion of algae, and then to have more fundamental approaches or whatever. But this time, this is the methodology. And finally, it's also related with omics. Yesterday, Elisa was talking about functionalities, how functionalities can be anticipated by the omic techniques. But this is the reason, because we need to integrate this photorespirometry and the studies that Anna already mentioned. We are able to measure the amount of nitrifying activity, the nitrifying activity, and then we need to find in the omics that we have the genetic or the enzymes related with this activity. But this is mainly to confirm, to establish or to validate the results with the origin. Okay? Because in my opinion, only to have one simple measurement is not enough. We need to be sure that if we are measuring some effect, it's because we have certain microorganisms or enzymes capable to provide these effects in the culture. Okay, I don't know if there is some other questions. Yes, Daniel?
Just a brief question, real quick. Why not normalizing by chlorophyll like you used to doing vertex?
Because the chlorophyll content of the biomass largely modified. And then if we normalize to chlorophyll, we are more or less reducing the amount of bacteria or whatever that we have in the culture.
Wait for the oxygen production.
It's oxygen production, but we want to normalize the oxygen production by the total solid that we produce. But as Anna already mentioned, the idea is to include these equations in the model, and the model will provide us the final biomass we will obtain. And including the model is capable to provide a certain percentage of bacteria and algae in the final biomass we are producing. Okay? Yes, that's all. Okay.
Okay.
Muchas gracias, Ana.
Muchas
Thank you very
gracias.
much.
Thank you.
Now is the time for Máximo.
Ahí.
Okay.
Aquí.
Ahí, muy bien.
No.
Pone mi nombre para Massimo Permissi. No, no, la aquí. Disco. Okay. Thank you. So, can you listen? Yeah?
Yes.
Okay. So, hello, I'm Massimo Pernisce. I'm working at ICM, Institute of Marine Science in Barcelona, as a postdoc, and I'm also in charge of the flow cytometry lab. And today we will talk about flow cytometry application in microbiology. I'm a microbial ecologist, so it will be more about ocean and sea and this kind of stuff. This is the title that I provide, and this is the fancy title that I prefer, that is a little bit more funny. And let's start. Flow cytometry is a technique that allows us to answer two questions: who and how many. And basically, we count bacteria, algae, and other microorganisms thanks to their optical property. We always start with a sample that is fixed or fresh. This makes a little bit of difference in the lecture, but not so much. And we have always our flow cytometer that does look like a box. And then we will try to see what is outside the box, inside the box. And inside the box, we have the flow. So basically, the machine took a liquid that is named sheet fluid. So it makes two little sheets to squeeze the sample and to have one cell of our sample that passes in front of a laser. Once the cell passes in front of the laser, it emits fluorescence, and we collect in graphs like that are named cytograms. So it's really important that just one cell pass in front of the laser. Because if we have more, of course, we don't have a proper measure. This machine was developed at the beginning to work with blood and things like that, and we adapted with time to working with the marine samples. So it's no one thought, oh, let's do this for marine biology. And once the cell passes in front of the laser, is excited, and so the information is collected by several filters of different color. Let's take a better look. We have a property that is named scatters. This is not fluorescence, it's how the light is deformed by your sample. Normally we have forward scatter. This is the scatter. If a cell is little like that, the light will divide like that. If it's big, it will be like that. So we can relate this property with the size of the cell. The more the cell is bigger, the more it will be bigger the scatter. We also have the side scatter. So how much light, blue light, go on the side in an angle that is from 90 degrees to less. And this information is more related with morphology and granulometry, and also with size. We saw that when we work with bacteria, this is better to characterize the population. And all these things that I will comment today, we will see later better at the machine because it's really more easy to see it doing. And after that, we have the fluorescence. There are two types of fluorescence. This an inner fluorescence of the sample. This is the most normal example. Is the chlorophyll A. So normally we have we know the excitation, in this case in blue light, and the emission in red light, and we have a filter that is represented by this rectangle. So the filter will collect just this part of the emission of fluorescence. We can also use stain that provide fluorescence to our sample. The one that we will use today is cyber green, that it is orange if you look at it, but it emits in green. And in this channel that is called FITS. And cyber green is a DNA stain. This means that it will stain also your DNA. So we always manage this with the gloves because you can have cancer with this. And the important thing is that the quantity of cyber green is proportional to the quantity of DNA and RNA of RNA and DNA of the cell. If you work with the microscopy, you have to understand that flow cytometry is really, really similar to microscopy, but the only difference is the work is done by the machine. But if something is green in the microscopy, you will read in green in the flow cytometry. Or if you see chlorophyll in the microscope is really red, and you will look for the red in flow cytometry. So I have a lot of students that came to the lab and say, I don't understand all these dots, all these things, but it basically microscopy, but in another way, you know. And normally the results are in this graph that we call a cytogram. As you can see, this is the same name of the channel. Every cytometer has different names. Sometimes you just see filter 1, filter 2, filter 3. And here we have the scatter. In this graph, each dot is one cell, in this case, bacteria. The last thing of this stain is not specific for bacteria. It's specific for DNA. So it will stain phytoplankton, bacteria, fungi, viruses. So it's the operator that has to know the sample to understand exactly what it's doing. You can also see that there is a little h near the name. So the sample in general, we can read it like weight of this peak of area of the peak. There are little difference, but they are not so important. Just to I explain this just for you to understand when you see this letter. Sometimes the area, you know, has a little second peak, so they are not completely proportional. And also the number of the axes are non-dimensional because this dot can move if we give more voltage to the machine. So it's not, you cannot think about flow cytometry like spectrophotometry. It's not that we say, oh, this is the quantity of chlorophyll, or this is, in this case, the size. No, it just, it moves, it's relatives. We know that something here is bigger than something here, or something here has more DNA than something here, but it's just a relative measure. There are ways to make it not relative, but in general, it's relative. And finally, how to decide what is a population. So we have a lot of dots. Sometimes it's really clear because you see a space between populations. So you say, oh, this is something and this is something else. But it's not always like that. There are two philosophies when the people make gate to leave a fixed gate always in the same position and just pass your sample and say, oh, this is what I want to count. Sometimes people just go one by one and do it like that. And also, normally we do things manually because you have a student and you ask to the student to do it. Now there are a lot of automated methods in Cytoflex, the cytometry that we will see today. You just can click automatic and it will make the gate. Otherwise, there are scripts with R or I guess also with Python to just say, can you please understand what is a population? And normally the results are expressed by the machine like event per microliter. And we normally in microbial ecology use cell per milliliter. We will see this also at the machine later. And this is the machine that we will use today, I hope. It's Cytoflex. Cytoflex, the one that they have at the university is really good because it has 7 lasers. You can see the laser here. And these are all the detectors the machine should have. So normally when you take the manual of the machine, you can understand how many colors can you use. We normally use only the fluorescent from red laser and blue laser, you see. For example, the cyber green need the blue laser to be excited and emit in green. And here you have the name of the channel, Fitch. But for example, people in biomedicine, they use a lot of probe, for example, when they want to study cancer and the different type of population in the blood of a person with cancer, they need more color to characterize different population. And when you have more color, of course, you have to be sure that this color doesn't overlap. And for this reason, we use the cyber green because in nature, we always have chlorophyll. So we need another color that doesn't overlap a lot with this one. I put this, I think you have also in the PDF. It's a spectrum viewer. So when you have to choose a color, for some reason, it's a good way and really fast way to say, oh, this doesn't overlap. And you can buy your stain or your product. And a little bit of characteristic of the Cytoflex. I'm really happy with this machine. I don't sell it, but I really think that is kind of the Ferrari of the flow cytometry in this moment because every university and center is buying the same machine because it really works well. The software is also really, really fine. And compared to the machine that there were before, it's amazing. There are a lot of laser and filters, as I said before. You have a max of 10,000 events per second for reading. So I say that you have to have just one cell. If you pass this threshold, you will have more than one cell in front of the laser. This means that when you work, you don't have to dilute, which seems a really stupid thing, but it changed your day, you know. And before it was like 1,000, so it's really good improvement. It doesn't work under pressure, so the flow is really regular. Before you really have to look at the water that have to be always at the same level. It makes the vortex by itself, which is really nice. And it has violet scatter. What I commented before was the blue scatter, which is the normal scatter of the flow cytometer. Violet has a narrow wavelength, so it's better to characterize really little population. Now there are a lot of people that work with viruses or vesicles, so it's a really nice things that this cytometer have this scatter, and you have just to mix to filter to have it. So it's quite easy and useful. And let's start to what kind of population we can measure with this machine. We will start with phytoplankton because was one of the first things that people start to do, because phytoplankton has a lot of autofluorescence. Normally, in a normal marine coastal sample, we saw 4 populations that fluoresce in red. or in some cytometry is named filter 3. So we have Pleurococcus, Synechococcus. These are both two photosynthetic bacteria. And after that, we have pico-eukaryote and nano-eukaryote. Bigger things like diatoms sometimes are really on the top. There is no resolution to see diatom, and they are too much big for this machine. But there are machines that are more specific for bigger organisms. One thing, when we say pico-eukaryote and nano-eukaryote, is a convention. It's not the normal sites that we intend pico and nano. We just saw two population, and we say pico and nano. Now the tendency is to say eukaryotes, and that's it, because you really don't know what is there. This is an important thing of flow cytometry, is to understand that it's a rough technique. You never go really into this. It's not like omics. You cannot say, oh, this is this specific group. But I think it's still really useful. Normally, we identify this thanks to Synechococcus, because it's the only one that has fluorescence in yellow. We will see later this also to the machine. And Pleurococcus is always the one under Synechococcus, and we know that eukaryotes are on top of that. At the beginning, they just have culture, so they know where everything goes in the graph. But if you really want to know what is something, you should use sorting, which is a flow cytometer that can select your population. And after that, you can take your sample and go to omics and say, oh, this is this species. So you always have a little bit of, you need a little bit of knowledge of your sample to understand what is there. Otherwise, everything is just bacteria or eukaryote. And this is a sample of bacteria stained with the cyber green. As you can see, here we have the forward scatter, here we have the green, and all these are bacteria. I put a little bit of bits here, which is this blue population there. These are little dots that we use first to see that the machine is working well, and also to have a really rough estimation of the size. In this case, I think these bits were 1 micrometer, so we know that all these things are less than 1 micrometer. We can also use this to more or less know the diameter of the bacteria, because we know the value here, and so we can do a proportion. In this other graph, it's the same sample, but you can see that it's green versus red. So sorry for the misleading, because I put the photosynthetic one in green, but these are the one that fluoresces more in red. And you can see that they really pop up from the rest of population. For us, it's really important to define what is photosynthetic, because normally you from the same sample, you do phytoplankton, and you see the photosynthetic part without compromising the sample. And after that, you want to know something about the no photosynthetic part. So we use it basically to put it away and say, oh, this is, I'm not interested in this moment. An interesting thing here is that we don't expect this population to be here, because this population shouldn't have red. And actually, if you take a look, I saw that it's really good to use cyber green, because there is no overlap with the chlorophyll, but there is a little bit of overlap. This is a really little bit, but it counts, because you expect your populations without chlorophyll to be here. But this little overlap make that the filter red took information also from the cyber green, and the population go in diagonal. We are not worried about that, because the things that are chlorophyll really go out this, but normally people apply a thing that is named compensation, which is the correction of the fluorescence spillover. So normally you just put green bead in the machine, and you say, I want this green fluorescence. Just take this green fluorescence. And so mathematically, the machine will put this population from here to here. We will not do this today, because in microbial ecology, we realize that we don't need it, and we prefer to not do it, because if you can work less, you don't do it. And another thing about prokaryote is that we always say two population in a marine system: high nucleic acidic bacteria and low nucleic acidic bacteria. I want to highlight that this happens in the marine environment. So you can always, it's not always true. For example, in Prodigio sample was not true at all. You have a lot of population, but coastal environment are kind of simple. And these two populations are, here you have two different samples. You can see that here you have a lot of high DNA contact bacteria. This is the low, they are less. And here you have a lot of low. So we assume that the high, since the stain is proportional, are more active because they have more RNA and maybe they are duplicate the DNA, so they are in phase of duplication. So we can use the ratio of high nucleic acid content versus low to have some information about the activity. This was in some paper they see that this ratio is proportional to the bacterial production, which we measure with the radioactive leucine. And so we believe in this, but still there are little things that never will be big. Even when they are really active, they will not go so up. So it's, again, it's useful, but it's not perfect. And another technique that I want to show you, because it's quite common, is the use of two stains, one for green and one for red with the propidium. And with this technique, we can establish the number of bad cells. So the propidium just go inside cells that have the membrane damage. So we can use, we stain the same sample with these two colors. And what happens is that if you see in red, the damaged cell will pop up from the rest of population, and you can make a ratio. This red is different from the red of chlorophyll. It's far red. It's a little bit moved. Again, there are critics also on this because sometimes the permeability of the cell is changed with the physiology of the cell. But also in this case, we see that there was a proportionality with the bacteria production. So we keep doing and believe it. Now, you can do this only with fresh sample, of course, because if you fix, everything is damaged, so the propidium will stay in the entire population. And we also can measure viruses, basically with cybergreen, but in this case, it's diluted in milliQ, and the sample is really more diluted than for bacteria. Viruses are also always on the left of the bacteria and top down, bottom down. And you will see that they are always like line of different quantity of DNA. Normally, we believe that the one that are with more DNA are viruses of eukaryote, and this part here near the garbage are viruses of bacteria. And this is, well, it's not so recent, but it's the last thing that we add to the toolkit. And I recently worked with fungi, but not in flow cytometer. And there are stains that we still didn't try in flow cytometry. We try only in microscopy that are specific for fungi, because fungi has chitin, and we have the chalcofluor. This is quite common. And also what we used here, which is in this red picture, is the wet germ agglutinin. And in this case was conjugated with Alexa 594. Of course, in this case, we were working with a culture of fungi. So we have here our DAPI, which is in just the nucleus. Here we have our probe because we were testing a probe that was in green. So we decided to have the same for the chitin in red. But if you work with a sample from, for example, an algae culture, probably you have to choose another color because there is no point to have red and red. It's really complicated for the eyes. But this is just to know that there are also a specific stain for the eukaryote if you want to characterize for example, protease flagellate and this kind of stuff. Where the topic is that no one just sit and say, oh, I have to make a protocol for this for now, because there are a lot of things to do, and no one put his energy in technique because it's time consuming. But there are ways to count. Also, people are still really used to rely a lot on microscopy. They don't like to. It seems like still too much flow cytometer, but things are changing. And now I will show you a little bit of data. This is a paper, is methodological paper that I published last year about automated flow cytometry. It's in the Mediterranean Sea. So I use this cytometer. It's different. It's a Curie. This is my face because I was desperate. Nothing was working. And this is the boat that we used, the Garcia del Cid, that was just dismissed this year. I think this was one of the last cruise that he did. So I took seawater from a tap, and that was connected to a pump that was at 5 meters, so I can do the surface. And this machine that we will see later better, it's an automated sampler. So I have a sample of bacteria each 15 minutes. So this is the machine. It's named OnSite. I think it has been developed recently from a startup in Switzerland. So basically, this machine, it's more like that. This is the nice one. So it takes sample from one side, and all this other tube is just to clean itself. So you take the sample, you stain it with Cymer green in the very same way that you do with your hands, and just move the sample to the cytometer. This is really useful to have a time resolution really narrow, which is for us is amazing. And you have a syringe here, which is the one that makes the job. So this is our results. Each dot is abundance of bacteria, like cell per milliliter. Here we have Mallorca, here is Barcelona. So the cruise was, we are always in the center and go like a flower, going back, like this. And you can see that you can really see different color. When it's violet, it's few bacteria. When it's reddish, it's more bacteria. So you can see that in the center, we have the green. When you move till the coast, it became blue. And when you move till Mallorca, it became yellow. So we have higher value of abundance near Mallorca. We have just this really strong abundance near the port there because we enter there. And the port is really a mess. And here you can see just the abundance of the station. So this is the central station. It was a little bit constant, but go down during the time. And every time that, again, we go to the coast, it was less than in the middle. This day we have a storm. I always cited this because it was really nice that the machine keep working during the storm. So for me, it was perfect because I go to the bed because I don't want to throw up, but the machine keep it and was like, and then the range of the data was so narrow that I know that it worked good because there was nothing that say what the machine have done, and this was really nice. And this was the first time that we used the machine. We are really happy with that. And also I pulled together all the day sample and all the night sample because you can also we see the information through space here, but you can see the information through time. And again, the abundance of bacteria during the day is slightly higher than the abundance of bacteria during the night. And another interesting thing is that this is still abundance of bacteria. So we go from station D to station S. We stay 9 hours here and go back. And this day was, you can see that there were really 2 water masses because when we go back after 9 hours, we go back to the abundance of before. The interesting thing is that this is the salinity of the area, so you can really know that these were two different water masses. And this happened also with when we go more near Mallorca, so it really doesn't change during the days, and we spend 3 hours here. Was really interesting because when you measure, you never go back to one place and you don't know, and you just believe that your technique is working. But we really saw how much flow cytometry it's rough, but it's powerful because it's you have a real data. And this is the arrival of the port. This is the last hour. It was really nice to see how much the port is dirty. Then terrible. And this is another set of data. This is not published yet. I went to Antarctica in 2000, well, 2 years ago. And the Antarctica is really important environment in the Earth. It influences the global climate and the global ecosystem. And in particular, the microbial community is really important for the primary production, because a lot of the global food web is based on the plankton of the Antarctica, and also is really important for the carbon sequestration. They calculated that 30% of global ocean uptake is taken in the Antarctica. So we found it really interesting to have a huge cover of this area, and we take sample for bacteria or for phytoplankton. This is a picture of the salinity and how much it varies along our cruise. We start on the top, which really huge value of salinity is 34.5. And it's go down and down because it's found more sweet water. On the offshore, it's a little bit more stable. This is the Hesperides. It's a military boat that we can use in Spain. And this is a real picture from the cruise. We go on land, and it was really nice. So the cruise lasts 2 weeks. So I have 2 weeks of sampling, and we took also temperature and salinity around the entire cruise. And so here I will show you just a little bit of the value of abundance, because I don't want to bore you, but this area was the beginning of the cruise. I don't want, we start and finish here. This is Deception Island. It's named like that because they think to found a huge island, but was empty inside. And you can see that the bacteria abundance really go up here and here. And the interesting thing is that both here and here, we have human presence, because the Spanish base is in this island. Here we have volcanic activity, which means a lot of nutrients. We also have penguins and sea lion, which means a lot of shit, which is food for microbial. And also there is this horseshoe shape that make the water really less in communication with the outside. And this makes really the abundance go up. So again, flow cytometry is, you can see that geographically, these data are really a strong meaning. So again, flow cytometry is really powerful to establish the bacterial abundance, and especially in an automatic way, because you can call this sample, but it's really complicated. And as I said before, we can use the forward scatter to have an idea of the relative size. So you can see that the sides change a little bit during the cruise, especially here in the south part, and we have a peak of huge cell here in Margaret Bay. And the size is a little bit more higher. There is more green here than here. The interesting thing is that if we took the offshore water, so all this sample, you can see that there is a really good relationship between the relative size and the abundance, which is expected because the K and R species, so we have a lot of species that are really little and few species that are really big. This relationship is broken in the inshore water, probably because there is so much predation of flagellate and things like that, that there is no time to see the relationship, but probably it's still there. And as I said before, we can so to the low DNA content bacteria and high DNA content bacteria, since these are the two main groups, the two graphs mirroring each other, because when one go up, the other one go down when you do. And I did it with, in this case, with bioinformatics, with a soft script from Flosson, is there. And we can use this abundance to calculate the activity of bacteria. And again, the activity change around the coast. It's a little bit big in this area and really huge here in the south. We can also use, take a look to the phytoplankton. In particular, I want to focus on this group. This group is cryptophyte. They have a lot of fluorescence in yellow, but we are sure that they are not Synechococcus, because Synechococcus is not in the Antarctic at all, and also they are really big. The important thing of the so where it's completely absent in the offshore water and is present only here. The important thing of this group is that if this group grow, it displays diatoms. So it changes the entire structure of a trophic web. So if there are more cryptophytes, like in this case, there will be more salps and less krills. So if we have less krills, this is a problem for whale naturally, because the whale eat the krill. So just with the again, the flow cytometry is really powerful because we can have insight on the entire trophic web just with a normal sample, and it was really nice to discover that. We were also lucky because we have a story now. And now this is just to know that exists. There are, if you think about the fluorescence as I talk about it, it can deconceptualize it as phenotypic characteristic, because if there is more fluorescence in red, there is more chlorophyll. If more fluorescence in green, there is more DNA. We also talk about the scatter, so it could be more bigger, more. So all these characteristics is like if you have an animal and say, oh, this animal has 4 legs and 3 eyes, whatever. So we can use this characteristic to calculate a diversity that in this case is a phenotypic diversity. And from all these characteristics can be put in a table. And from this table, we calculate for each group of cells this diversity. This is all these techniques now are grow and grow. They go under the name of computational cytometry. It's something like what happened in the last 10 years with omics. So now there are a lot of people that are developing new scripts and new tools to make this calculation, both to identify group and to calculate diversity. So the diversity calculated for this set of sample, it was really nice because it goes from blue, green, and red. And it was surprisingly proportional with salinity. So salinity will explain the variability of alpha diversity in this case. These dots, well, they explain me later that they didn't put on the machine, so they are there, but they are not real. And yeah, and this is the salinity. So you can see that the change of the salinity really mirror the change of our sample. So of course, the salinity changed because there is the global warming, and this global warming really affect the microbial community. So the interesting things is that we can catch this change with flow cytometry. So in general, every change in parameter like temperature and salinity is reflected in the community and it easily detected with flow cytometry. So I was really fast or what?
No,
Okay.
20 minutes, but then we have time for questions.
Okay. So from one sample, we have information about the total abundance, group abundance, because you can see high DNA bacteria, low DNA bacteria, photosynthetic bacteria, the relative size, the biomass side for so if we can calculate the diameter of each cell, there are equations that can change the volume of this cell in biomass. It's not perfect, but I mean the equation of the carbon is really good, but there we are still adjusting how to calculate the diameter of the cell because we use the beads and the light really trespass the beads in a different way because cells are more translucent. So when you see this is less than 1 micron, is not exactly true. We can have information about the activity doing the ratio of high and low, and we can also now have information about the diversity. This diversity, I forgot to say that they say empirically that is not equal to the diversity that we calculate with 16S, but the pattern is the same. So we still believe that it works. And that's it.
Okay, thank you. Thank you, Maximo, for the excellent presentation. Very well presented and very dynamic. We have time for questions now. Yes, Belén.
Check the bacteria cells are alive for that can also be used for the microalgae.
I think you can use it for the microalgae. I never did it just on the sample of microalgae, but I think there is no problem.
And the other, the cytometry, you can just interesting to combine the omics.
Yeah, so I just sailed from Vigo to Canary and we took sample to make the extraction. So I took the sample from the same tap water and we want to back check because you know when someone want to sell you the technique, say it worked, but we are not sure 100% is quite new. So we want to sequence the 16S and make the diversity with cytometry and see if more or less is the same. It shouldn't because flow cytometry is a phenotypic diversity and it has also the information of the physiological state of the cell. So if a bacteria is in division, it will go up in the graph and will look like another population. But for 16S, it will be the same because the 16S is the same if the cell is dormant or dividing. So, you know, this is basically it's analysis of images. You know, you will see how much dots are in the same area. So we expect the same pattern, but it not has to be 100% equal. But the important thing that you can see where the change happened, and maybe if you have a lot of sample but you don't have money and you want to decide where should I sequence to see difference, you can use the diversity from flow cytometry to say, oh, here and here I'm sure that it will be different. Like for example, the one that we see from with the bot, you know, there is no point to do 10 point here and 10 point here. You can do 1 and 1.
More questions, Daniel?
In for the presentation, you mentioned that it is a Ferrari, and I agree, it's a very nice instrument, but it's also a very concentrated.
Yeah.
Do you see any efforts for making it simpler and more and cheaper for other applications instead of?
No. No, we have the other one, the one that I use on the boat, it's really cheap. It's 4,000 euro. It's, I mean, cheap. scientific chip. But it's really broke continuously. And
Ones are very expensive.
the good one is really expensive. And they are really, I mean, if you want a sorter is 10,000. Yeah, yeah. But I think it's good investment. It's also sometimes you feel better with the machine just because the software is it works better, and I always have to also teach to students how to use it, and I found that I realized that it's really easy for the student to use it, so I'm happy also for that. But it's a powerful machine. Maybe you can have it with less. You have the one with a lot of laser, but we have just 4 laser, I guess, and basically we use 2. So we put the near ultraviolet because we want to see DAPI sample at microscope and flow cytometer. But in the end, we never did it. Then you get animated and say, let's do this, and you see the sample with DAPI and say, this look like a shit. I prefer cyber green, and so you just keep doing things as always. But yeah, I think it's a really good machine, this one.
Because I was speaking that maybe you using for regular routine conflow of microbial culture.
I think for regular things is you can use something like the Alcuri because it's that you need the blue laser and the red laser and that's it. And Alcuris look like a Lego machine. It look like Meccano. It's really it's light. You can move it wherever you want. We put on the boat. We put both, and they work now the automatic sample they developed also for the Cytoflex. So we don't know, but we can use the Cytoflex in the lab because it's better. So
Antonio, please.
Besides the cost, I mean that well traded.
So the well-trained operator, it's me, and I mean, my boss, Pep Gasol, was really good in flow cytometer in the fax era. And I arrived to the lab after the pandemic, and the cytometer were into the box. And no one teach to me because, there was no... I have a little bit of training for the automatic sampler because it's complicated, but not for the cytometer itself. But I mean, you have just to read the manual. It's everything there. I think for example, you can understand how the machine work. They give you a little bit of training at the beginning. I didn't have it, but I've trained on other cytometer. So I think the machine more and more are user friendly. So because they want to sell it and they know that people want to do things fast, and I think Cytoflex is really, really easy to use, but it's like 100, 150. But I think flow cytometry, for this reason, I always say that the boss that are lazy send the student to flow cytometry, because you can always put 2 conditions and say, oh, more bacteria here, less bacteria here, because it's really easy. You can be a master, less than a master student, and use flow cytometry properly.
I have some questions related with these points. The price, more than the price, is the comfortability of using this equipment, as you mentioned, is becoming better. And my question is, there is a regular equipment, or it is possible to find one equipment that be able to help us to monitor the prevalence of eukaryotics, bacteria, eukaryotics, viruses and fungi, at least to explain, to have a look to the evolution of these populations. And then if we detect that in the cultures we have a crash or whatever, to be able to correlate and to say, oh, there was this tendency, and then to take samples and to send the samples to the omics guys in order to have a more detailed analysis of the...
Yeah, so I think for this kind of things, the automatic sampler is really, really good. And this work both with Akuri and Cytoflex. I don't sell it, but I'm really happy with the company because they really help you to each part of the things. And it's a little bit more complicated because you have to prepare solution and know that everything is in this place. But I mean, you can do it. It's not nothing.
But
And so about the groups, you can do normally. We did it. We did for now phyto bacteria. We also did the double staining every 50 minutes. What we don't know how to do it is eukaryotic that are not fluorescence, because I start to play with stains, but I have to see there are stains that are specific for flagella, for example, or stains that are specific for a component of the eukaryotic membrane. So you can say, oh, this is not bacteria, this is another thing. But I need time to do it. In general, no one do this because it's so easy to do it at we for example at our institute we have automated microscopy. So we use a probe for eukaryote, and it passed from sample to sample. So for now we didn't put effort. You can also use fish, but in this case it's more elaborate because there are people that do fish in cytometry. But in this case, I think the goal is to find something that is like cybergreen, but for eukaryotes.
But what about viruses, etc.?
No, virus you can do it.
We can do that.
I think
the same equipment we can detect
Yeah.
using the
Yeah.
stains.
Yeah.
Okay. And the second question, because your experience in this type of samples, etc., in the natural samples, which is the damage of phytoplankton related with fungi or viruses? Because we always assume that fungi are the most problematic for microalgae. But in our collaboration in Prodigio, we detect a lot of viruses in the cultures, and we don't know what happened with the viruses.
Yeah, we'll actually start to study fungi now at the institute, so we have no expertise in flow cytometry. We use it a little bit of omics. And viruses, I think there are papers that show a correlation between the numbers from flow cytometry of phytoplankton and huge viruses. The problem with viruses that it's even more rough than bacteria because you really don't know what infects what. So it's more complicated. But there is a correlation. I mean, I think that yeah. I can pass you some paper later. About fungi, people not work a lot with that in flow cytometry for now. I add the stain because I think, oh, we never tried. I think yesterday we should try this to see if we can see fungi in natural environment. But there is a lot of work to be done.
I think the flow cytometry, as you say, is very valuable to explore this kind of interactions as a first step to be later in a deeper analysis using omics, because at the end omics must be the reference.
Yeah.
Yes.
The fact that it's omics, I think the big difference is that cytometry is fast and omics is not fast. And sometimes you don't have this time. And it's also a lot more expensive. So I think it depends on what you want. Maybe if you know that you always have a fungi things, you can start to see the fungi on your graph. Sometimes another interesting thing is that population have fluorescence in the wrong channel. You don't know why, but you can see population where shouldn't be there. Maybe you are liking your fungi is there. You can say, oh, when this dot appear here is because there is something. You never know. For this reason, I think you have to know your system to define population.
Yes. Antonio, please.
Yeah. It's related to the experience that you had. You talked about environmental sampling. Yeah, but when you move to filtration, for example, algae filtration, can you see the differences in screening the biological established? For example, you had something highlights, I don't know, fungi, this kind of viruses, because we talk about this kind of project,
I mean, I don't work a lot with culture, and if we work with culture, it's little things that we have in the lab. Sometimes you expect that your culture is really poor, and you see a lot of shit, and you can see when the culture is going down. And the people at my institute normally to monitor the culture fast, they use this. So I have a friend that work with some Aptophyte. I don't remember the name of the things. And he every day he just took a little sample and take a look because he want to be sure that he just take it to the fluorescence. He know where if you have a fixed gate and all the parameters are the same, you expect to see your population always in the same position. So if you go down, there is less chlorophyll, and this means that maybe the health of the culture is it changed for some reason. I don't know if I answer. You mean difference with the environment or difference in the
environment? Which are the highlights that you suggest to look it up?
I mean, if you highlight in the sense of environmental parameter or in the machine, I don't understand your question. Oh, well, I will always temperature and salinity. I mean, there is no oxygen, but you know.
But I think we need to compare still the data from the reactors with the data from the natural environment, because we didn't compare yet this as part of the Prodigio project. We are only focusing in the influence of operational conditions in the evolution of the population. The problem and the advantage of the Prodigio project is that we have plenty of data. Thousands of samples, thousands of results from these samples, because we analyze the omics, the flow cytometry, the chemical fingerprint, the composition, the detailed composition of the supernata. The problem now is how to manage this information and how to combine. We are in this process now.
I think there is with flow cytometry, if the sample is too much complex, it's really difficult to understand what are you saying. You don't have a way. You can just sort the population and sequencing and say this is this. But of course, you cannot do this always. For this reason, if you have always the same closed system, you can understand more or less, and you know what is there. If it's an open system, it's a little bit more complicated. Yeah, but I tell because I saw it's prodigious, really complex sample. I don't know why, and they came from the reactors. There were a lot of things that appear a lot. I mean, a lot of population, and normally I just do this cruise now, and for 3 weeks, bacteria move, but you have high and low from Vigo to Canaria. So it's really, well, it's like, I don't know, Anna was talking about this yesterday at the dinner, that, it's like a zoo, and you give a lot of food, and maybe the animal will be different that in the environment. I don't know.
Yeah, interesting though. I think
No way, we can talk later also.
This tool is about the screening. So if you had a father during the time in your culture, it could be identified, for example, are risky or a tendency during the time. I think that it's not an easy work to do, and I think also Daniel wants the intention to having a pattern during the time.
Another way to do this is with the calculation of the diversity, because it's look like something that is ecological, but if you spot change in diversity in general, you don't need to know that this thing is changed, but something is changed, and you can check and say, oh, I will do omics now. And you can more or less automate this, I guess.
Thank you, Maximo. Thank you for all the speakers, and of course you for attending these lectures, and the people that also attend the lectures online. We finalize these formal lectures. Now we have the coffee. We need to take another picture here. Please, the participants that are online, please switch on your camera in order to take a group picture, and we will later perform the training activity.
Bye-bye, Gabriel. Thank you. Bye-bye.
Bye.
Bye-bye.
Bye.